to welcome everybody to this first GGI Tea Breaks colloquia of the normal series, because we had a special event 2 weeks ago on the Weinberg legacy. It was a great success, and I just want to thank again all the speakers and the participants for that event. Now we start the series of this year, and we start with cosmology. We had a great name among the cosmologists, Eiichiro Komatsu, and I leave Guido for the introduction, and thank you to the speaker.
Okay, welcome everybody. So today's speaker is Eiichiro Komatsu. Among cosmologists, he definitely doesn't need any introduction. He works both in theoretical and observational cosmology, and is the director of the cosmology division at the Max Planck Institute in Garching since about 10 years. He's known for his part in the WMAP mission when he was still a student, and then he was a professor at Austin, and then he moved to Germany. His topic of today will be how the CMB can help us constrain new physics, and in particular, he has his new measurements on cosmic birefringence, which may prove to be very exciting. So the stage is yours, Eiichiro.
Thank you very much. Thank you for the invitation. Thank you for coming. Do you see the cursor here or not?
Yes, we do.
You do? Oh, excellent. Okay, good. Good. So yes, I'm going to tell you about our very recent work on cosmic birefringence. So this talk is based on 2 papers. One is this one that appeared about 1 year ago. The other one just appeared 3 weeks ago. So it's a very new work. And let's hope that we're seeing some hint of new physics. So I'd like to start by motivating the work. So it's pretty well known that standard cosmological model requires new physics. We don't know what the dark matter is. We don't know what the dark energy is. We don't really know exactly how initial perturbation was generated in the era of cosmic inflation. What is the fundamental physics behind it? And my argument, and not just me, many people agree that the polarization of the CMB may hold the key. And there are 2 things. One is today's topic, cosmic birefringence, may tell us what dark matter and dark energy actually is. And then for early universe part, it's now famous that B-mode polarization of cosmic microwave background can tell you something about cosmic inflation. So let's put it in this way. So we have an observatory over here. This is a light cone. So as you go farther away from you, you are looking into the more distant past. And this is the moment when universe became transparent. So this is when photons decoupled from the cosmic plasma when temperature was 3000 kelvins. This is the surface of last of scattering. Now, scattering creates polarization. This is the moment that cosmic microwave background photons acquired polarization. Now, you can use this observed pattern of polarization to learn something before this surface of last of scattering. That would be the topic of the early universe, what powered the Big Bang, what's the fundamental physics behind cosmic inflation. You can also have dark matter and dark energy influencing this photon propagation, and that will be today's topic. Yeah. Question: how does the electromagnetic wave of the CMB propagate in space filled with dark matter and dark energy? We typically imagine that you have this oscillating direction of electric field that it's a direction of the polarization, remains the same as photons travel 13 to 14 billion years until they reach us. But why can't photons' polarization direction change? Okay, why can't the plane of linear polarization rotate as photons travel pretty big distance, right? 13 to 14 billion years is a lot of time. So we have been thinking about how to do this measurement, and it's a difficult measurement. And then I'm going to present to you latest results of such measurements. But I just wanted to tell you that we are also excited about the method that we developed. And it took us 2 years to develop the methodology. And if you ever have done the data analysis, results are sexy, but the efforts that went into the preparation of methodological developments, validations against simulations, yada, yada, yada. I mean, that's pretty significant. I just wanted to make this point. Yuto Minami, junior scientist in Osaka University in Japan, is a real hero behind all this, okay? So, physics. It's been pointed out since almost 30 years ago that when you have pseudo-scalar field that couples to the electromagnetic tensor in parity-violating way, it does something interesting to photons, okay? So there are a lot of stuff here. Let me just go step by step. Of course, this F mu nu is the usual electromagnetic tensor. A nu is the vector potential. Then when you write down the relationship between usual electromagnetic fields and vector potential, you can convince yourself that this usual kinetic Maxwellian term here is parity even because B is magnetic field. That's pseudo vector, hence parity even. You square the parity even quantity, that's still parity even. E is a vector, so it's parity odd. It changes the sign under the inversion of spatial coordinates. But if you square it, it's still parity even. So as promised, this Maxwellian term is parity even. The physics of electromagnetism doesn't care whether you look into the mirror or not. But this new term here called Chern-Simons term, FF dual, right? This FF dual is written this way. E here, epsilon here is a totally anti-symmetric tensor. And you can convince yourself that that's parity odd. In fact, it's -4 times B dot E because E changes sign under parity, it's a parity odd. If you wanted to keep this term as parity even as a whole, this theta, a scalar field multiplies it, has to be a pseudo scalar, which also changes sign under parity. Now, if you're not familiar with particle physics, you may stop here, right? Oh, what is this? I don't care. It sounds really weird. We don't know anything like that in standard model. That's not quite true. In standard model, we have a pion. Pion is a pseudo scalar that has parity odd. That was discovered in late 1950s. And it's not apparent, okay? So you have QCD Lagrangian that doesn't look like this for electromagnetism. But as Weinberg showed, you can write the effective Lagrangian for pions. And then in this effective Lagrangian, this Chern-Simons term appears. And in fact, thanks to this term, pion can decay, neutral pion can decay into 2 photons, okay? So it's in standard model. Now, in this particular paper that Turner and Woodrow wrote, pseudoscalar is an axion. And this axion field can be dark matter or dark energy. So thanks to this term, okay, the space filled with dark matter and dark energy, which is a pseudoscalar, which couples to electromagnetism just like pions. This term can make phase, this term violates parity. So it makes a difference between right and left-handed polarization states in a way that it makes phase velocities of right and left-handed photons different. That will lead to rotation of the linear polarization direction. So birefringence, right? If you shoot the laser, which has a definitive polarization direction initially, laser goes into the crystal, and this crystal has a property that depending upon the oscillation direction of electric fields, or actually the polarization states, right or left-handed polarization states of the waves, the refractive index of crystal is different. So that will change the phase velocities of right-handed, left-handed photons. So you have the laser light goes into the crystal, and as photons go through the crystal, linear polarization, plane the linear polarization rotates, okay? So it's seen even in daily life physics, okay? So why can't universe filled with dark matter, dark energy behave like that? So let's recap standard Maxwell theory as a warm-up. If you write down line element using conformal time instead of the physical time, eta, then Maxwell, so this propagation equation for vector potential in this particular gauge conditions obeys wave equation just like in Minkowski space-time. Okay, even if it's an expanding space, equation motion for AI looks just like Minkowski. Deep reason is that its electromagnetism is conformally invariant. So for all conformal, all the metric that's conformal to Minkowski, equation motion looks exactly the same. Now, let me go to the Fourier space. K is the propagation direction of photons. Then I have a right-handed frame, okay? So the thumb is direction of the photon, so it's K, that you have X and Y. So then I define right-handed polarization, circular polarization states as A plus, and then left-handed, the other one, as the A minus. Now, let me use this magic of zoom now, okay? So I'm a source. I have right-handed, stuff here. And from the source, this is right-handed, okay? From my point of view, it's clockwise rotation. From your point of view, the observer, it's a counterclockwise rotation. Yeah, I hope that makes sense to you. This becomes important later, some stupid detail of how measurements are done, okay? Now, if you then do the dispersion relation, okay? So, solution looks like a plane wave. Now you have the angular frequency for plus and minus modes. Vacuum doesn't distinguish between left and right. So you just have dispersion relation that's equal for right and left-handed states. No surprise so far. Now let's add Chern-Simons term. This distinguishes between right and left polarization states. So equation motion gets modified, and as a result, the dispersion relation gets modified. Now let's then complete the square, ignore the second order term, take a square root. That's phase velocity, and as promised, phase velocities of right and left-handed states are slightly different. Then this means that you take the difference between them, okay? This term, by the way, is absolutely tiny. Absolutely tiny. This term can be at most the ratio of the wavelengths of photons that we observe to the size of the horizon today. So this is like 1 centimeter divided by 14 gigaparsec. It's absolutely tiny. But photons propagate for 13 to 14 billion years, okay? So the difference between them is absolutely tiny, but this accumulates. And this, so even if at any given instant, okay, over the period of photon, this is an absolutely tiny effect, but this just slowly accumulates and finally becomes observable. Yeah. So, okay, look, this sun here is a plane of linear polarization rotation as defined by the International Astronomical Union. That's what observers, astronomers use all the time. So here you go, right-handed frame, thumb is propagation direction of photons. For me, right-handed, right, rotation. For you, it's a counterclockwise rotation. CMB scientists, however, decided to use different convention since 1997. And therefore, for CMB scientists, positive rotation angle means clockwise rotation. Okay, let's remember this, okay? Therefore, when you see positive beta, this is not right-handed circular polarization state. It's actually opposite, okay? And it's interesting, you know, this subtlety has never been an issue until now because this doesn't really affect anything that we have seen so far, like temperature power spectrum, temperature E mode polarization power spectrum, B mode power spectrum. It's only this parity-violating combination, E mode, B mode cross, or T and B, that this matters. Okay, so just wanted you to know. All right, so therefore, long story short, when you have this kind of convention for Chern-Simons term plus coefficient, scalar field, FF tilde, then beta is given by this formula, notice minus sign here. So that's the results. And then larger the distance the photons travel, larger the effect that becomes, okay? So this becomes important as we describe our methodology to determine this beta. But this beta is what we are after. So why study the cosmic birefringence? The universe energy budget is dominated by two dark components, and they can be axion-like pseudo-scalar field. So detecting parity-violating effect tells you that dark matter and or dark energy is parity-violating stuff. That's a breakthrough. I forgot to mention one very important thing. Here, this whole thing vanishes if theta doesn't depend on space-time. That is an easy way to understand that. This FF dual is a total derivative. So if you integrate this Lagrangian density over the space-time invariant volume, it vanishes. It only gives you the surface term, unless coefficient depends on space-time. Let's say it's dark energy, it's spatially homogeneous, then only thing that matters is theta time dependence. So in order for this to do anything to observable, theta has to depend on time, which immediately implies that if this were dark energy, you would instantly rule out cosmological constant. And this will instantly tell you that this is quintessence-like, slowly evolving pseudo-scalar field, okay? And that will probably have a big implication for fundamental physics. Okay, but you know, I mean, that's too complicated for me. I'm a very simple-minded person. I learned in school that weak interaction violates parity. Why can't the universe violate parity? Okay, if we have one thing that violates parity, why not universe? Let's look. So this is a full sky image of the temperature fluctuations in the CMB observed by Planck satellite. And it's polarization, okay? So the lines, directions indicate the direction of polarization, and lines length will give you the strength of polarization. Now to quantify, to probe parity violating physics using this, you need to come up with eigenstates of parity. Okay, so we now decompose this into Fourier modes. L now is a Fourier vector. And then we decompose this polarization pattern into two patterns, one called B mode polarization, namely the direction of polarization is either parallel to or perpendicular to the Fourier vector. B mode is 45 degree tilted with respect to the wave number direction, and E is parity even, B is parity odd. It changes sign, okay? Now, I acknowledge the abuse of notation here. These E and B modes are jargons used in CMB community. They are not related to electromagnetic fields. And I know it's confusing, okay? So I just said that electric field is parity odd, then magnetic field is parity even. Here, E mode is parity even and B mode is parity odd. Okay, so just swallow that. That's the way it is. Don't ask why. Now, E is parity even. If you square the amplitude to get the power spectrum, it's still parity even. B is parity odd. But if you square that to get the B mode power spectrum, that's parity even. Temperature E mode cross correlation, that's also parity even. TB, EB are parity odd. So if the universe conserves parity, then TB and EB should vanish. If you see any evidence for non-zero TB, EB that's cosmological, well, that's a discovery of parity-violating physics. So here's the power spectra, temperature power spectrum, E mode power spectrum, B mode power spectrum. This is the B mode power spectrum coming from gravitational waves that I briefly mentioned at the beginning. We don't talk about this, but we want to find this. So far, all the B mode we found is coming from the conversion of E to B by gravitational lensing. Now, but today's topic, of course, is TB, EB correlation power spectra, which are not shown in this plot, okay? Typically, these are ignored. So we're talking about extracting new science out of the data that weren't really conceived before. So by rotating the plane brilliant polarization by beta uniformly across the sky, observed E, observed B, will be given by the intrinsic E and B at the surface of lots of scattering times the factor that depends on beta in this way. So these are all complex formula in if you go to this way, right? EB, not instead of E plus minus IB, that's complicated. Then you have a mixture of E and B, okay, through beta. Beta is small. Okay, so you can say E observed is basically E intrinsic minus 2 times beta times B intrinsic and so on. Then you can form EE power spectrum, BB power spectrum in EB power spectrum and relate all of them. So EE observed is written this way, BB observed that, EE observed that. Then you can relate now EB observed to EE observed to BB observed so that everything is written in terms of observable. There you go. Okay, so EV generated by the difference between EE and BB observed plus intrinsic, if any, EB correlation out there. Now, it actually makes sense that EB is given only by the difference between E and BB power spectra. The reason is the following. EB, okay, this beta doesn't create anything. It just mixes E and B, okay? It just changes the relationship between EB we observe and EB that was out there at the surface of loss of scattering. So you need to have asymmetry between E and B because if there's equal amounts of E and B, mixing them doesn't do anything, okay? Mixing them just, for example, if you have randomly oriented polarization directions in the sky, this will give you equal amounts of E and B mode power spectra and no EB because there's no parity violation in the random orientations of polarization directions. Imagine now you uniformly rotate randomly oriented polarization directions in the sky. They remain random. So as granted, right? As a result, if you didn't have any asymmetry between E and B initially, you're not going to create EB, even if you, no matter how many times you rotate the sky, it doesn't really matter. Yep. And luckily, in our universe, there's a large asymmetry between E and B. This is the key. And this is that allows us to measure this signal. So far, so good. Why hasn't there been a detection of this until now? That's a miscalibration of detectors. Okay, so photons traveled for a long, long time, and they may be experiencing this rotation of plane of linear polarization. But when they now reach our telescope and come to the detectors, if we rotated the detector with respect to the sky, but we didn't know it, okay? So for example, I have a telescope, I have my detectors, I carefully made, and I went to the bathroom. Somebody came and they rotated my focal plane, okay, just for fun, just making fun of me. I came back, I didn't know that was rotated. I look at the sky, oh, there's an EV correlation. Well, that was the fact that I didn't know that my detectors are rotated with respect to the sky, okay? Not the polarization. Real polarization was rotated with respect to the last scattering surface. This is the lack of knowledge of our detector system. That kills you, okay? So unless you know what the detector orientation is, alpha, only thing you can ever measure is the sum of the two, alpha plus beta. So you somehow have to know what the alpha is. And that explains why there has not been, there are lots of measurements so far, okay? But there has not been any discovery yet. So initial measurement was done by Feng et al. In 2006. I thought that was a really cool physics, so decided to look into this. But then the thing got a little more complicated. So there's no detection at that time. Then, yeah, but now recently, you see, there's a lot of detections. And Planck, it's 6 sigma. And Polarised, -3 sigma. And SPD is, I don't know, 15 sigma, but the values are completely different and so on. Okay? So because this is not beta, this is alpha plus beta. Somehow you have to know alpha. And for example, for WMAP, we knew that we couldn't tell we couldn't really calculate our detectors below 1.5 degree. Okay, so we had this intrinsic uncertainty of calibration, plus minus 1.5. Quad correlation at 0.5 degree. And then really, I mean, Planck had this 0.3 degree, so this is not significant anymore. It's not 6 sigma, right? It's 1 sigma. And this experiment didn't deliver the estimates of the uncertainties of calibration. In fact, they used these EV correlations to calibrate their detectors. You know, they thought that these were actually their calibration angles. Okay, so what should we do? So the key is the realization that cosmic birefringence is proportional to the path length of the photon. In sky, okay, so I showed you, but it's a bit cheating here, okay? So it looks as if everything is CMB. Well, if you actually look up at sky yourself, you realize that there's a Milky Way. Milky Way has lots of gas. Gas is polarized, and gas emission is polarized. So you have a lot of polarized emission coming from the Milky Way. Milky Way size is only 100,000 light years. So these polarized light, okay, comes to us traveling only tens of thousands of light years, not 14 billion years, okay? Sorry, yeah, that's right. So they traveled only tens of thousands of years, not 14 billion years. So birefringence, if any, is minusculous. You can completely ignore it relative to what you would find from CMB. So you can now use, okay, the fact that foreground gets rotated by alpha, but CMB gets rotated by both alpha and beta. Okay. Then if you do the algebra, you discover that EB observed is the difference between measured E and BB And so you don't have to know, by the way, foreground E or BB. That's a very beautiful thing, okay? You can relate everything you see in EB to the observed difference without the model, okay? E and BB. But we know something about C and B, okay? It's not that we are clueless about C and B. We are clueless about foreground, but we are not clueless about C and B. We know a lot about it. So we can actually use our knowledge of C and B to distinguish between alpha and beta. So CMB gives you alpha plus beta, and we use foreground to get alpha, and we break the degeneracy. But there's one important thing. So there's an intrinsic EB correlation of a foreground, and intrinsic EB correlation of a CMB. Yeah. What do we do with them? First of all, we are going to ignore intrinsic CMB EB at the surface of loss of scattering. Why? Because discovery of intrinsic EB at the surface of loss of scattering is equally exciting. And we just leave that fun for future. Okay. For now, we focus on birefringence and leave intrinsic one for future exercise. Like a dessert, okay? Keep the dessert until we're done with the second course. We're not there yet. This foreground EB cannot be ignored, and I will talk a lot about that later. Okay. So how does this work? Let's understand the physics behind this using simulations. I have simulated maps of 120 gigahertz, 200 gigahertz, 240 gigahertz, and 340 gigahertz. And we have a Milky Way dust. Dust intensity increases as you go to higher frequencies. So this is CMB dominated. And then as you go to higher frequencies, dust dominates. Now, this is beta, vertical axis beta, horizontal axis alpha. CMB gives you alpha plus beta very precisely because you can see CMB so bright that when you are seeing one of those CMB dominated channels, this vertical, the diagonal line is alpha plus beta constant. That combination can be measured to infinite precision. That's why contour here looks like a line. Yeah. So even though 120 gigahertz is dominated by CMB, it still has a lot of dust in it. It's not a non-negligible amount of dust. That's why you can also measure alpha using foreground. Contour closes, and you can break the degeneracy between alpha and beta. Now, if you go to higher frequency that has more dust, you can measure alpha better. Okay. If you go to a little bit even higher, you can measure dust even better. So it helps to shrink the error, okay? But then if you go to 340 gigahertz, that's completely dominated by dust, you don't see CMB, then you can determine alpha very well, but you're not gonna get any beta at all because you don't measure CMB. Therefore, you cannot measure even alpha plus beta. You see this very interesting synergy between low and high frequencies that you can use to your advantage to break the degeneracy. Took us a while to develop this methodology, and we finally applied this to Planck data, and we found that there's a 2.4 sigma hint for this positive beta. Okay, fine, 2.4 is 2.4. Let me explain a little bit. Okay, so we used Planck public data release 3 from 2018. We used 4 high frequency channels, 100, 143 to 17, 353. Essentially, dust is your enemy here. And then if you, for example, assume that Planck detectors are perfectly calibrated, so alpha is 0, then you get, I don't know, 6 sigma detection of beta. But of course, as I said, that's not a real 6 sigma because we don't know what the alpha is. But now we apply our methodology, we break degeneracy, then our uncertainty is now 0.14. And it turns out that the Planck detectors are fairly well calibrated. Okay, this alpha for each frequency. Okay. Oh, looks nice. Can I see that by eyes? Okay, so as I said, the observed difference between E and BB power spectra is what gives us the hint. This red is the measurement, so it's total CMB plus foreground, blue is the CMB. So difference between them is the foreground. Difference between red and blue gets rotated into alpha. Blue is rotated both by alpha plus beta. Then if you look at ED, okay, this red is what you can interpret as alpha, and blue is what you can interpret as beta. Okay, so the thing is, because this foreground is bright at large angular scales, as you go to lower multiples, it gets boost. Okay, so in EB, therefore, if it's due to miscalibration of the instrument, you see blowing up signal of EB that we don't see. Lack of EB at such low multiples is the evidence that Planck detectors are pretty well calibrated. Okay. Okay, good. Now, what about CMB? So if you compare this acoustic oscillation of that's characteristics of CMB, okay? I don't know about you, but you know, if I like blur my eyes, do the smoothing of data points by eyes, acoustic oscillation emerges, no? Well, maybe not. Fine. Okay. it's I don't know, 2.4 sigma. So anyway, this is more like trying to verify that our codes don't have any bugs. Okay. Sanity check. What about foreground? So in our methodology, we're basically saying anything you see here is due to the miscalibration angle. But if foreground has intrinsic EB, then part of alpha that we see is coming from foreground itself. So if we define gamma is a new angle that corresponds to the foreground EB, then using foreground, we don't measure alpha. We actually measure alpha plus gamma. Sine of gamma is the same as the sine of a foreground EB. So if foreground has positive EB, gamma will be positive. Foreground gives you alpha plus gamma. CMB gives you alpha plus beta. You take the difference. Now our method gives you beta minus gamma, not just beta. Okay. If gamma was positive, if we make a correction due to the intrinsic foreground, beta increases. Therefore, our measurement would be a lower bound to beta. What's the sign of gamma after all? So there was evidence, surprising evidence actually, that dust emission has positive intensity dust E polarization and positive dust density B correlation. Okay, people didn't expect to see it, but in dust somehow they had this correlation. Then we expect positive EB dust. So we expect positive gamma. So beta increases. That's where we ended a year ago. We wanted to verify that our methodology works in general, and then foreground can be under control. So we decided to work with Planck people. And then I'm very proud that this paper was led by two PhD students. One is Patricia Diego Parazuelos, University of Cantabria, Santander. Here, she's smiling. And then Johannes Eskild, PhD student in University of Oslo. So these are double corresponding authors. And famous Yuto Midami here. Yeah. So this was really led by junior people. I'm super happy about that. So we used Planck data release 4. And this has better overall noise level. It's lower noise and better characterized instrumental systematics. Okay. So we expect that error bar will shrink. Okay. Then we try, in order to test the foreground effect, we try now 4 different, actually, full sky data and 4 different galactic masks. that looks like this. This is the full sky result that we reported in Minami and Komatsu, but then we progressively cut more sky as to see what foreground does. Okay. So first of all, this time, these 4 people, so Matt Tristram in Paris is a permanent staff member there. So these 4 people developed 4 independent pipelines. Okay, and they all got the same answer. So there's no bug in the code anymore. And the result was 0.3 plus minus 0.11. So error became smaller from 0.14 to 0.11. Significance increase. Now, my experience, okay, my limited experience as a person who does data analysis, usually if the signal is a fake, statistical fluke, as you make more innovation in data analysis, significance goes down. That didn't happen here. Okay, as we make more sophisticated analysis, significance goes up. It's still below 3 sigma. So, okay, fine, interesting, but what? Okay. Then, so these 4 different colors corresponds to the 4 different pipelines. It's full sky. Then, as you go to mask more sky, beta decreased. Okay, they became negative. This was foreseen. Okay, let me tell you that if foreground has a positive EV, it's a lower bound to beta. Okay, so once you make a correction of that, you recover positive beta. So let me explain what I mean by that. So if you have foreground intrinsic EV, foreground intrinsic EV can be written this way. That's the term we need to consider now. Okay, we took account of this, not this one yet. Cosine for alpha here, sine for alpha here. Well, that sounds familiar. Use trigonometry functions and write this in terms of sine for alpha plus for gamma. That's a new angle defined by ratio of this and that. Okay, trigonometry formula. As promised, Foreground now gives you not just alpha, but alpha plus gamma, where gamma is given by intrinsic EV divided by E minus dV of the foreground. Then, I already showed you this slide, okay? So if gamma was positive, beta would be only a lower bound. So a surprise discovery of TB correlation from the Planck, okay? We don't know where it came from, okay? Because at first it's weird, right? Why should dust break parity? Okay, and but in any case, regardless of the origin of TB, it seems reasonable that EB is proportional to TB, and that assumption alone can undo most of the dust effect. But that's not really satisfactory. So let's go to the physics. Where does this come from? Okay, so let's imagine that you have. If you look at radio sky, 21 centimeter, hydrogen emission, okay? Hyperfine transition of hydrogen ground state. Then you discover that there's a thin filaments everywhere, okay? We don't really know where that comes from either, okay? But let's say filaments, and then you look at, so filament contains a lot of dust, it's hydrogen. So along the filament, dust is like, whoa, shining, no? Wow. Then if this, so that's the dust filament, and you see lots of emission coming from dust. If magnetic fields, so this vertical direction is a magnetic field direction. If magnetic field is aligned with filament, dust grains, which are not spherical but elliptical, ellipsoid, dust grains align with the magnetic field such that major axis of dust grains is perpendicular to the magnetic field direction. So dust polarization direction is perpendicular to the magnetic field direction, okay? So if you want, you see lots of these little horizontal line everywhere along this filament. That's E, okay? Because E polarization is to the you have the polarization directions which are either parallel to or perpendicular to the wave number of Fourier mode. E positive, no B. In this case, you don't expect any TB correlation. So that's not what we're seeing in the real universe. If for some reason magnetic field lines are misaligned with respect to the filament like this, then there's a 45-degree tilt component with respect to the wave vector. You generate B, okay? It's TB correlation. And because E is still there, positive, EB is also positive. Well, that's cool, but let's think, okay? It cannot be the case that in the entire sky, misalignment, the filaments are there and they are misaligned in the same direction. Just cannot happen, okay? So if you ask me, okay, in order for this to work, it has to be that there's a chance cancellation, okay? So you have basically in the ideal world, basically all these misalignments, left and right, they should all cancel. But in our universe, it so happens that if you mask the sky in some degree, there is a residual TB or EB that's not perfectly canceled. It's just a chance, okay? Residual, yeah. That's probably what we are seeing here. So let's anyway do this something super reasonable. I say EB is proportional to TB. Okay, that is misalignment of magnetic field. Okay, so let me first say EB is proportional to TB. Amount of EB is proportional to EE. That's all. Okay. Then we have free amplitude that varies slowly with L. That's all. So it's a free parameter here. Amplitude shape is fixed by E dust power spectrum and TB dust power spectrum. Physically speaking, what this says is that misalignment between magnetic field and hydrogen filaments is psi. That's a ratio of TB and TE dust, and the amplitude is given by EE. Once you say that, then gamma is given by this formula. So essentially gamma is given by TB. That's completely reasonable to me. Then tada, you undo, okay? If you account for that using free parameter amplitude A, you undo this effect. So our expectation was completely correct. If you correct for dust TB, beta increases. So you take the full sky result, which is least impacted by this correction, okay? The amount of correction you make is the smallest here. Beta now went up from 0.30 to 0.36. Uncertainty didn't change. There was enough constraining power in data. Statistical uncertainty, okay? Formally, this is 3.3 sigma, okay? So for the first time, it exceeds 3 sigma. Brand new results that just came out 2 days ago. So one of the corresponding authors, Johannes Eskild, had this brilliant idea. Why can't we use the data we have to probe frequency dependence of beta? After all, cosmic birefringence, okay, by pseudo-scalar field. This will predict frequency independent, photon energy independent birefringence angle. But if you had a Faraday rotation, it should go like 1 over frequency square. Well, if you had effective Lagrangian that violates Lorentz and CPT invariance, then dispersion relation can be modified to give you something like beta goes like nu squared, okay? So there's some astrophysics in it and fundamental physics in it by looking into this important index N here, power index. And to do this, Johannes found that maybe using only 4 channels wasn't enough. Maybe we should also add lower frequency data that Planck had, 30, 44, 70. So this is the first analysis that used all of 7 polarized frequency channels of Planck for determining beta, and he found that n is comfortably consistent with 0. Okay, so, and if you look at this, it's beautiful. it's amazing, and by including lower frequency data without correcting for foreground, it's still more than 3 sigma, and error bar went down from 0.11 to 0.10. Doesn't seem like a huge improvement, okay? But when you're talking about 3 sigma effect, every 10% in the error bar matters, okay? So you are thrilled to have reduced error bar from 0.11 to 0.10. Okay. Now, another thing. We talked about dust. Dust affects these 4 data points, not this. These are affected by synchrotron radiation, okay? So if foreground was doing the job, you wouldn't find, well, okay, fine, error bars are big, but you wouldn't find frequency independent results. I mean, okay, of course you could by chance, but that's not something you would expect a priori. So that seems good. Okay, but of course, 3 sigma is 3 sigma, okay? I have seen enough 3 sigma in my life that went away. It's still entirely possible that this is just a statistical fluke. But as I said, at least what I've seen is that if it's a statistical fluke, as you make more innovation in data analysis, significance goes down. Here, as we make more innovation in data analysis, significance keeps going up. Let me confess that plus minus 0.11 is a statistical only uncertainty. As a faithful, reliable data analysis, we must come up with a way to assign systematic uncertainty. Until we have plus minus 0.11 plus minus systematics, we're not very comfortable. Okay, so that's something we're working on. Good news that I didn't tell you really much about. This new processing of Planck data came with really realistic simulations that include all known instrumental systematics of Planck data sets. Using that simulations, we're able to find that known systematics have negligible impact on the measurement of beta. So at least we can just ignore that, okay? Of course, it is always possible that there are unknown instrumental systematics, but at least we can say known systematics doesn't matter. So we could just focus on understanding foreground part, no evidence for frequency dependence. So if the measured beta is indeed confirmed as cosmological, you have a very important implications for fundamental physics behind dark matter and dark energy. What's next? Okay, so you might think that somehow we have to make progress on foreground. That seems hopeless. This was a desperate attempt, okay? We had to do this because Planck instrument had calibration uncertainty that was too big. Next step is easy. Next time we do experiments, we calibrate instruments better, okay? We have a target now. If we wanted to have 5 sigma detection of 0.3 degree, we just have to calibrate our instruments better than 0.06 degree. That's it. Then you can forget about our methodology that relies on foreground. You just go out and use CMB to measure beta. Okay, that's all. So why don't we just do that? And then let's hope that this evidence or hint for 3 sigma hint for new physics continues to remain. I stop here.
Thank you, Eiichiro. And hopefully, yeah, this can be very exciting in the future. So now I ask if there are any questions. Please raise your hand or just speak. Okay, Glennis, please.
Hey, Eiichiro, that's really good to see you. It's really wonderful that you're pushing this data that way. I had 2 questions. One was, of course, I'm interested in this foreground problem. Well, one was that, why do you assume that the a possible calibration uncertainty is frequency dependent? If I properly understood you, that is the frequency dependence that is your handle on the effect. But the calibration could be perfect. It seems to me it could be frequency dependent. So that was the first question.
Calibration is frequency dependent. All these alphas are not just frequency, but also detector sets.
Oh, okay.
Yeah. So we're simultaneously determining all of these alpha and beta at all frequencies.
Oh, okay.
Yeah.
Okay.
Yeah.
Okay. And the other thing was having to do with the last escalate analysis that you showed. Had you dropped the first two data points where, as you were alluding, the galactic foreground could be most complicated. It looks to me like you could fit it with a nu to the -2 if you only had the last
yes.
5.
So Eskild's a paper, actually, that's the first thing he presents. He doesn't use these data points.
Okay.
And then still the n is completely consistent with 0.
Well, maybe, but with huge error bars, it might be consistent with -2 also.
Okay, we have actually a very good answer for that. So chi-square difference, okay, because that's all that matters in the end. So the chi-square, delta chi-square between n of 0 and n of -2 is 2.25, okay? So you're right. It's not completely excluding it. It's not preferred, okay?
Well, what are the chi-squares, not the delta chi-squared, right?
It's a delta chi-square. So delta chi-square.
Right, I'd like to hear the chi-squares, then I can judge whether it's a significant delta chi-square.
No, it's a delta chi-square. So it's absolute. So if delta chi-square was 4, it's 2 sigma. If delta chi-square was 9, it's 3 sigma.
Well, that's right. But if the underlying chi-squared was 1,000, we would say that, you know, it was not something we could use.
Oh, that's not correct. No matter how big the chi-square.
Well, theoretically, but in experience, we know that if it's a horrible fit, then you can't, you know, theoretically, if it were a Gaussian distribution, et cetera, what you say is true, but in practice.
Yeah, it's a perfectly good fit. It's a perfectly good fit, yeah. So what I'm telling you, and you are right, okay? So if we don't model foreground, n equals -2, Faraday rotation is disfavored only with delta chi-square of 2.25. Okay, so this is not even 2 sigma. You are right. Okay, if we model the foreground, then delta chi-square goes up to 3, but not yet even 4. Okay, so you are right about that. Yeah.
Still, you pioneered a wonderful direction of investigation. Thank you so much.
Okay, there is John.
Hello, Professor. Beautiful talk and analysis. Thank you very much. And this is John here. So I had one comment and a related question, which is if you compute the sort of natural size of beta, I believe in your normalization, coming from a single axion, it ranges from 0.05 to 0.1 is the sort of the reasonable, not reasonable, is the expected range. This is when the axion moves over the entire field range it can, so FA. And as you know, it's independent of FA. It's one of the wonderful things. So your 0.3 is a little bit on the high side. Of course, you know, it's an order 1 number, an order 1 difference. Okay, so the first thing to say is it's in order of magnitude, it's in exactly the right range you'd expect from an axion.
No, I saw your paper, and you are like 10 to the -3, right? And indeed, this is more like 10 to the -2 level. Yeah.
Well, no, actually, there's another factor which is taking in. Your thing is only, I'd say, about a factor of 3 larger than we would say.
Okay, yeah, I think that's right. I think that's right. Yes.
But there's one thing that comes in, which is, as we pointed out, that if you have, and you expect many axions to be doing this evolution because it's a large range, then you get a root n enhancement. But then that leads to the following question: is whether you can see, you should be able to, if it was possible to do redshift tomography of this change, then you could see really striking, you know, evidence for the multiplicity and understand why this total rotation angle is larger, but also get much more information. It'll be very hard for other physics to do. So.
Excellent. Okay. We can do really bad tomography. Okay. This high LE mode comes from the surface of lasso scattering, redshift of 1000. This bump here comes from reionization. It's redshift of 10. They experience different path lengths of the photons. So we can measure independently beta from here, beta from there, take a difference and do tomography, okay? So if there is any difference between them, that means that field, let's see. So, okay, because in terms of the conformal distance, distance to redshift 10 is almost the same as the distance to redshift 1000, right? So if the field is slowly evolving, we expect them to be basically the same. But if the field starts to oscillate just around time of reionization, then we expect no EB here, but a lot of EB here, okay? So that we can do, okay? So maybe, I don't know how interesting that is for you, but that kind of measurement is completely possible. And we're actually now almost done with the draft on that by solving Boltzmann equations. That's good news. Bad news is Planck data doesn't yet allow us to use low L data yet. So we are restricting our analysis to L of 50 or above. So we're completely blind to the reionization bump at the moment. But for future experiments, I'm sure that we must do that to do the tomography.
Yes, I think it's very important. Thank you for your answer.
Yeah, great. No, thanks. Yeah.
So there's a question by Valery Rubakov in the chat. Can you use a TB instead of EB?
So yes, yes and no. So in the WMAP era, okay, here, this measurement was exclusively relying on TB. And when you can show, I showed it in this paper, when the noise level of the polarization is bad, okay, TB is most sensitive. But when polarization noise becomes better, EB is far more powerful than TB, okay? So yes, you could do TB, but doesn't add anything. That's why we are just relying on EB. Yeah, that's the answer.
Okay, yeah, I hope Valerie is satisfied. Anybody else? Do you have any questions? I have one question. So what do you think is the next important step in this measurement? Should we wait for LightBird, or do you think something can happen before?
Oh yeah, I mean, if we can calibrate an instrument, anyone can do this, okay? So you just have to calibrate it, that's all. Simon's Observatory, Atacama Cosmology Telescope, Southpaw Telescope, Bicep, you name it, you know? Just calibrate the instrument. Forget foreground, okay? This was a desperate attempt, okay, to get science out of the Planck data. But, you know, if you're excited about this measurement, just do the calibration and go for it. Yeah.
Interesting. Okay. Any other questions? Comments? So there is one in the chat. What's the best resolution that you expect on beta?
The error bar, yeah?
Yes, I guess.
So this would be completely limited by your calibration uncertainty, okay? So it's no longer statistics. Statistics would be perfect, okay? You can get zero uncertainty in alpha plus beta, okay? You see, this error bar is tiny, okay? So it's all about alpha, okay? And how can you calibrate alpha? Currently, because there's no need before, best alpha is 0.5 degree, okay? Here, okay? Now, Planck is better because they had detectors calibrated, but then assume that some of the calibration errors are random. So when you co-add data, that gets reduced, okay? But, you know, how do you calibrate even? Okay, so what you do, you have an instrument you built, then you put an artificial polarizer somewhere far away with known direction, hopefully. then you observe it, and then you see whether orientation of the polarization you observe is the same as the orientation of polarization you put. You may be surprised to hear that making this artificial polarization source better than half a degree is a challenge. But I'm sure that if there is a need, people will get it. I'm very sure about that. Okay, so all we need is, I think, a good reason to invest time and money on making better artificial polarizers. Now, another thing. Okay, you need to put this in a far field. When you have a 1 meter dish, okay, of the telescope, far field is a few hundred meters above. How do you put polarizer few hundred meters above? Use drone. Okay, that's the new technology. You use drone with excellent altitude controller. How do you call it? The position, control. Then just fly that damn thing with great calculator on top, and then just observe the drone and you do your measurements before you make a measurement of the CMB and go back and forth. It's done. Yeah. So there's a group of scientists in Chile who are making this drone calculator for all the telescopes in Chile. Okay. Last time I heard about this, they already at the level of 0.1 degree. Okay. That's great. Okay. So that's already enough to at least verify our 3 sigma results. Okay. So if they can already do this calculation, plus minus 0.1, that's 3 sigma. Okay. If they can push this a little further to 0.06 degree, that's 5 sigma. So I hope there's enough motivation to push the technology further. I mean, CMB has amazing track record of revolutionizing technology. So I think we can do it.
Oh, okay. Thank you. That was a really nice talk. Can I ask one more question?
Yeah, sure.
Oh, okay. So I saw that the beta that you considered is not actually, it's a constant over multipole L.
Very nice.
I was just wondering if it can be a function of L and if your analysis could be able to detect that if it is.
Absolutely. So if it's dark energy, okay, where should I go? So if you look at this formula, okay, it looks like it's a partial derivative integrate over time. It turns out that this is total derivative. Okay, so what that means is solution is theta observed minus theta emitted, including spatial variation. Okay, so you can actually measure field. This is proportional to basically the so this is the axion field. Okay, so theta emitted is basically the field at the surface of lots of scattering. So they vary, of course.
Right.
Yes, you can totally look at it. In fact, this is easier to look at it because this is something that varies over the sky. So this is not degenerate with calibration angle. That's why all these experiments, this Namikawa et al., Bianchini et al., and a few others looked precisely at the spatial variation instead of looking at isotropic ones. And they didn't find any signal yet. But this definitely improves as we have better noise level, better data sets. So yes, you're right. It has to go hand in hand. And let me even tell you one more exciting thing. Let me come back, okay? Here. So this was about theta emitted spatial variation. What are theta observed, okay? So this will be theta observed minus theta emitted. If theta was a dark matter, it oscillates around the potential minimum today.
Right.
So this first term oscillates the frequency that's comparable to the duration of the experiment. So if you do this time domain measurement of beta, So far, we are averaging over entire duration of Planck, right?
Yeah.
But for example, bicep people looked at in time order data, okay, time variation data, they didn't find anything, but that's also very exciting. It's many innovative ways that you can do data analysis to look for time variation, spatial variation. After that, isotropic signal. I think there's tons that you can learn that way.
Okay, awesome. That's really exciting. Thank you.
Thank you. So any other questions? If not, we thank Eiichiro again for a very nice talk and presentation, and we will publish his slides immediately. And if you have other questions, there will be the question and answer section on the website. Thank you very much.
Thank you very much.
And see you next time.
Yeah, hope to see you all in person.
Yes, hopefully, yes.
Yeah.
Thank you.
Bye.
Very
Bye.
much. Thank you.
Ciao,
Bye.
ciao.
Bye.
Bye.